Have you ever wondered if mathematics could completely shatter your understanding of reality? Well, buckle up, because today we're diving into one of the most mind-bending theorems in all of mathematics, the Banach-Tarski paradox. A mathematical result so bizarre, so counterintuitive, that it seems to suggest you can take a single sphere, cut it into pieces, and reassemble those pieces into two identical spheres. Yes, you heard that right. One becomes two. Something from nothing. Magic? No. Mathematics. Welcome back to the channel, and if you're new here, make sure to hit that subscribe button because we explore the most fascinating corners of mathematics, science, and logic. Today's journey will take us through a mathematical wonderland where our intuitions about space, volume, and reality itself get turned completely upside down. The Banach-Tarski paradox isn't just some abstract mathematical curiosity. It's a theorem that reveals fundamental truths about the nature of infinity, the structure of space, and the limits of what we can actually measure. By the end of this video, you'll understand why this paradox has puzzled mathematicians for nearly a century, why it doesn't actually violate conservation of mass or energy, and how it connects to some of the deepest questions in mathematics and physics. So grab a cup of coffee, settle in, and prepare to have your mind blown. Because once you understand the Banach-Tarski paradox, you'll never look at spheres, or mathematics, or reality itself quite the same way again. Let's start with the seemingly impossible claim. The Banach-Tarski paradox states that you can take a solid ball in three-dimensional space, decompose it into a finite number of pieces, and then reassemble those pieces using only rotations and translations to form two balls, each identical to the original. No stretching, no squashing, no adding material. Just cutting and moving. This sounds absolutely insane, doesn't it? It seems to violate everything we know about conservation of matter, about volume, about basic common sense. How can one thing become two things without adding anything? It's like claiming you can take an orange, cut it up, and reassemble the pieces to get two identical oranges. But here's the thing. This isn't a magic trick or a thought experiment gone wrong. This is a rigorously proven mathematical theorem, published in 1924 by Stefan Banach and Alfred Tarski. It's not a paradox in the sense of being a contradiction. It's called a paradox because it contradicts our intuitive understanding of how space and volume should work. Now, before you start planning to solve world hunger by duplicating food, let me be clear about something crucial. This theorem exists in the realm of pure mathematics, specifically in a branch called set theory. The pieces we're talking about aren't physical pieces you could actually cut with a knife. They're mathematical sets with properties so strange and abstract that they couldn't exist in our physical universe. Think of it this way. In mathematics, we can define objects and operations that have no direct physical counterpart. We can talk about infinite sets, imaginary numbers, spaces with infinitely many dimensions. The Banach-Tarski paradox lives in this mathematical realm, where we can manipulate objects in ways that would be impossible in the physical world. The paradox relies on what mathematicians call non-measurable sets. These are sets so pathologically constructed that we can't assign them a meaningful volume or measure. It's like trying to paint with a color that doesn't exist in the visible spectrum. The mathematical machinery exists to describe it, but it has no physical reality. So why should we care about something so abstract? Because this paradox reveals something profound about the nature of mathematics itself, about infinity, and about the relationship between mathematical truth and physical reality. It shows us that our intuitive understanding of space and measurement, while perfectly adequate for everyday life, breaks down when we venture into the infinite and the abstract. The Banach-Tarski paradox is a window into a mathematical universe where the impossible becomes inevitable, where our common sense not only fails, but fails spectacularly. And understanding why it works will give us insights into some of the deepest questions in mathematics and philosophy. To truly appreciate the Banach-Tarski paradox, we need to understand the mathematical landscape that made it possible. This story begins in the late 19th and early 20th centuries, during what mathematicians now call the foundational crisis of mathematics. For centuries, mathematicians had been developing increasingly sophisticated theories about infinity, sets, and measurement. But as these theories became more powerful, they also revealed troubling contradictions and paradoxes. Mathematicians realized that their intuitive understanding of mathematical objects wasn't sufficient for the rigor they were trying to achieve. One of the key players in this story is Georg Cantor, whose work on infinite sets in the 1870s and 1880s revolutionized mathematics. Cantor showed that there are different sizes of infinity, that some infinite sets are larger than others. His work was initially met with resistance and even ridicule from some mathematicians, but it eventually became the foundation for modern set theory. Cantor's ideas about infinity were crucial for what would become the Banach-Tarski paradox. He showed that infinite sets could have counterintuitive properties. For example, an infinite set could be put into one-to-one correspondence with a proper subset of itself. This seems impossible at first glance, but it's a fundamental property of infinite sets. The next crucial development came from Felix Hausdorff in 1914. Hausdorff proved what's now known as the Hausdorff paradox, which showed that the surface of a sphere could be decomposed into pieces and reassembled to create two spheres with the same surface area as the original. This was already pretty mind-bending, but it applied only to the surface of the sphere, not the entire solid ball. Hausdorff's result relied on a principle called the axiom of choice, one of the most controversial axioms in mathematics. The axiom of choice states that given any collection of non-empty sets, you can choose exactly one element from each set, even if you have infinitely many sets and no explicit rule for making the choices. This might sound innocuous, but the axiom of choice leads to some very strange consequences. It allows mathematicians to construct sets and prove theorems that seem to violate our intuitive understanding of mathematics. Many mathematicians were uncomfortable with it, but it proved so useful for proving important theorems that it was eventually accepted as a standard part of mathematical foundations. Enter Stefan Banach and Alfred Tarski in 1924, building on Hausdorff's work. They proved that the same type of decomposition could be applied not just to the surface of a sphere, but to the entire solid ball. This was the birth of the Banach-Tarski paradox as we know it today. Stefan Banach was a Polish mathematician who made fundamental contributions to functional analysis and measure theory. Alfred Tarski was also Polish, known for his work in logic, set theory, and the foundations of mathematics. Together, they created one of the most counterintuitive results in all of mathematics. Their proof was purely theoretical, relying on abstract mathematical constructions that had no direct physical interpretation. But it was rigorous and correct, and it revealed something deep about the nature of mathematical infinity and the foundations of geometry. The mathematical community's reaction was mixed. Some were fascinated by the result and saw it as revealing important truths about the nature of infinity and measurement. Others were disturbed by its implications and saw it as evidence that something was wrong with either the axiom of choice or our understanding of mathematical foundations. This tension continues today. The Banach-Tarski paradox remains one of the most striking examples of how mathematical truth can diverge from physical intuition, and it continues to generate discussion and debate among mathematicians and philosophers. Now let's dive into the mathematical machinery that makes the Banach-Tarski paradox possible. Don't worry if some of these concepts seem abstract at first. We'll build them up step by step, and by the end, you'll see how they all fit together to create this amazing result. The key mathematical concept underlying the Banach-Tarski paradox is something called a group action. A group in mathematics is a collection of symmetries or transformations that can be combined in well-defined ways. Think of all the ways you can rotate a cube while keeping it looking the same. These rotations form a group because you can combine any two rotations to get another rotation, and every rotation has an inverse that undoes it. A group action is what happens when a group acts on some mathematical object, like a set of points in space. For the Banach-Tarski paradox, we are interested in how certain groups of rotations act on the points of a ball in three-dimensional space. The specific group that makes the magic happen is called the free group on two generators. This might sound intimidating, but the concept is actually quite beautiful. Imagine you have two basic operations. Let's call them A and B. You can perform a B, or the inverse of A. Or the inverse of B. You can also combine these operations in any order. A followed by B, or B followed by A, inverse, or any other combination you can think of. The key property of a free group is that no non-trivial combination of these operations gives you the identity operation, except in the obvious cases. In other words, there are no hidden relationships between A and B. They're completely independent or free. Now, here's where it gets interesting. It turns out that the group of all rotations in three-dimensional space contains a free group on two generators. This was proven by Felix Hausdorff and is sometimes called the Hausdorff paradox or the free group lemma. What this means is that we can find two specific rotations of three-dimensional space such that all combinations of these rotations and their inverses are distinct. No combination cancels out except in the trivial cases where operations are explicitly undone. This property is crucial for the Banach-Tarski paradox because it allows us to partition the points of a ball into different sets based on how they transform under these rotations. Some points might be obtained by applying operation A to some fundamental set, others by applying operation B, still others by applying A followed by B, and so on. The free group structure ensures that all these sets are disjoint. No point can be obtained in two different ways. This gives us a way to decompose the ball into pieces that don't overlap. But wait, there's more. The same free group structure that allows us to decompose the ball also allows us to reassemble the pieces in different ways. We can take the pieces that were created by applying various combinations of A and B and rearrange them using different combinations of these same operations. And here's the kicker. Because the free group structure is so rich and flexible, we can actually rearrange the pieces to create two copies of the original ball. The free group contains enough room or degrees of freedom to allow this doubling. This is where the mathematical abstraction becomes crucial. In the physical world, we're used to thinking about pieces as having definite shapes and boundaries. But in the mathematical world of the Banach-Tarski paradox, the pieces are much more abstract. They're defined not by their geometric properties, but by their relationship to the group action. These pieces are so pathologically constructed that they don't have well-defined volumes in the usual sense. They're what mathematicians call non-measurable sets. You can't meaningfully ask what their volume is because they're too irregularly distributed throughout space. This is why the paradox doesn't violate conservation of volume in any meaningful sense. The original ball has a well-defined volume, and each of the two resulting balls has the same well-defined volume. But the intermediate pieces that we use to perform the transformation don't have well-defined volumes at all. It's like asking about the total weight of all the prime numbers. The question doesn't make sense, because prime numbers aren't the kind of things that have weight. Similarly, the non-measurable sets in the Banach-Tarski construction aren't the kind of things that have volume in any meaningful sense. Now that we understand the mathematical tools involved, let's look at how they're used to prove the Banach-Tarski paradox. The proof is quite intricate, but we can understand its main strategy and key insights without getting bogged down in technical details. The proof proceeds in several main steps, each building on the previous ones to construct this seemingly impossible result. Step 1 is to establish the free group structure within the rotation group. As we mentioned earlier, this involves finding two specific rotations such that all non-trivial combinations of these rotations and their inverses are distinct. This is the mathematical foundation that makes everything else possible. The rotations typically chosen are rotations around two axes that are positioned at an irrational angle to each other. The irrationality of the angle is crucial because it ensures that no finite combination of these rotations will bring you back to where you started, except in trivial cases. Step 2 is to use this free group structure to partition most of the ball into disjoint pieces. We divide the points of the ball based on their history under these rotations. Some points are in the fundamental domain, meaning they haven't been moved by our rotations. Others are in the A orbit, meaning they're obtained by applying rotation A to some point in the fundamental domain. Still others are in the B orbit, the inverse orbit, and so on. The free group structure ensures that these orbits are all disjoint. A point can't be in both the A orbit and the B orbit, for example, because that would imply a non-trivial relationship between A and B that doesn't exist in a free group. This gives us a way to break up most of the ball into pieces that don't overlap. I say most because there are some special points, like the center of the ball and certain points on the axis of rotation, that need to be handled separately. But the vast majority of the ball can be partitioned this way. Step 3 is the clever part. We use the same group operations to reassemble these pieces in a different configuration. Instead of having all the orbits combined into one ball, we rearrange them to create two separate balls. Here's how it works. Take the A orbit and apply the inverse of rotation A to it. This moves all the points in the A orbit back to the fundamental domain. Similarly, take the B orbit and apply the inverse of rotation B. Take the inverse orbit and apply rotation A, and so on. When we do this systematically for all the orbits, we find that we can reconstruct two complete copies of the original ball. One copy consists of certain orbits reassembled in the original position. The other copy consists of the remaining orbits reassembled in a different position. The key insight is that the free group structure provides enough redundancy to allow this doubling. Because there are no non-trivial relationships between the group elements, we have complete freedom in how we rearrange the orbits, and this freedom is sufficient to create two copies from one. Step 4 is to handle the exceptional points that couldn't be included in the orbit decomposition. These points form a countably infinite set, which means they can be handled separately using a different technique. It turns out that any countably infinite set in three-dimensional space can be partitioned into two sets, each of which has the same cardinality as the original. This allows us to deal with the exceptional points without breaking the overall structure of the proof. The final result is that we have successfully decomposed one ball into a finite number of pieces and reassembled them into two balls, each congruent to the original. The entire construction uses only rotations and translations, with no stretching or distortion of any kind. What makes this proof so remarkable is not just its conclusion, but its method. It reveals deep connections between seemingly unrelated areas of mathematics: group theory, measure theory, set theory, and geometry. It shows how abstract algebraic structures can have concrete geometric consequences. The proof also illustrates the power and the strangeness of the axiom of choice. Without this axiom, the construction wouldn't be possible because we couldn't make the arbitrary choices needed to define the non-measurable sets. But with the axiom, the impossible becomes inevitable. This is why some mathematicians remain uncomfortable with the Banach-Tarski paradox. It's not that the proof is wrong, but rather that it reveals consequences of our mathematical foundations that seem to conflict with physical intuition. It forces us to confront the fact that mathematical truth and physical reality don't always align in the ways we might expect. At this point, you might be wondering, if mathematicians can prove that one ball can become two balls, why aren't we using this to solve resource scarcity? Why can't we just duplicate food, or gold, or any other valuable commodity? The answer reveals important distinctions between mathematical abstraction and physical reality. The first and most important point is that the Banach-Tarski paradox deals with mathematical objects, not physical ones. The balls in the theorem are perfect mathematical spheres existing in idealized three-dimensional space. They're made up of mathematical points, which have no physical substance. When we cut these balls, we're not making physical cuts with knives or saws. We're partitioning abstract sets of points based on their mathematical properties. The pieces created by this process are not physical pieces that could exist in our universe. They're what mathematicians call non-measurable sets, and they have properties that are impossible for physical objects. For example, these pieces don't have well-defined volumes, surfaces, or boundaries in any meaningful sense. They're scattered throughout space in such a complex, irregular way that they can't be physically realized. Think of it this way. You can mathematically define a set consisting of all points in space whose coordinates are irrational numbers. This set is perfectly well-defined mathematically, but you could never build a physical object corresponding to it. You can't make something out of purely irrational points because atoms. Molecules and all physical structures have rational relationships to each other when measured in any physical unit system. The second key point is about the role of infinity. The Banach-Tarski construction crucially depends on dealing with infinite sets of points. Each piece in the decomposition contains infinitely many points, and the rearrangement relies on manipulating these infinite sets in very specific ways. Physical objects, however, are not made of infinitely many point particles. They're made of atoms, which are discrete, finite entities. Even if we could somehow perform the mathematical manipulations described in the theorem, we'd be working with finite collections of atoms, not infinite sets of mathematical points. Moreover, the quantum nature of matter introduces fundamental limits on how precisely we can locate and manipulate particles. The Heisenberg uncertainty principle tells us that we can't simultaneously know both the position and momentum of a particle with perfect accuracy. This quantum fuzziness makes it impossible to perform the kind of precise point-by-point manipulations that the Banach-Tarski construction requires. The third important consideration is the axiom of choice. As we discussed earlier, the Banach-Tarski paradox depends crucially on this axiom, which allows us to make infinitely many arbitrary choices simultaneously. In the physical world, however, we can't make such choices. We can't reach into an infinite collection and simultaneously select one element from each of infinitely many sub-collections, especially when there's no rule or algorithm for making these selections. Some philosophers and mathematicians have argued that the axiom of choice should be rejected precisely because it leads to counterintuitive results like the Banach-Tarski paradox. However, the axiom is so useful for proving important theorems in other areas of mathematics that most mathematicians accept it despite its strange consequences. From a physics perspective, there's another important consideration: conservation laws. The laws of physics include strict conservation principles for energy, momentum, angular momentum, electric charge, and other quantities. These laws have been tested extensively and have never been found to fail in any physical process. The Banach-Tarski paradox doesn't actually violate these conservation laws because it operates in a mathematical realm where such laws don't apply. Mathematical points don't have mass, energy, or charge, so there's nothing to conserve. The paradox shows that mathematical volume isn't conserved in the construction. But mathematical volume isn't the same thing as physical volume, which is related to the amount of matter present. If we could somehow perform a Banach-Tarski-like operation on a physical object, we would need to account for all the energy, momentum, and other physical properties of the atoms involved. Now, the mathematics tells us nothing about how to do this, because it operates at a level of abstraction, where these physical properties don't exist. There's also the practical consideration that even if the paradox could somehow be applied to physical objects, the complexity of the construction would make it utterly impossible to carry out. The non-measurable sets involved in the decomposition are so pathologically complex that describing just one of them would require more information than could be stored in the entire observable universe. Finally, it's worth noting that the Banach-Tarski paradox actually helps us understand the limitations of mathematical models when applied to physical reality. It shows us that mathematical abstractions, no matter how rigorous and beautiful, don't automatically correspond to physical possibilities. This is an important lesson for anyone trying to apply mathematics to understand the natural world. The Banach-Tarski paradox is just one member of a family of related results that reveal the strange properties of infinite sets and non-measurable objects. Understanding these variations helps us see the broader mathematical landscape in which the paradox sits. One of the earliest related results is the Hausdorff paradox, which we mentioned briefly earlier. In 1914, Felix Hausdorff proved that the surface of a sphere can be decomposed into pieces and reassembled to form two spheres with the same surface area. This was the precursor to the full Banach-Tarski result, dealing with surfaces rather than solid objects. The Hausdorff paradox might seem less dramatic than Banach-Tarski, but it's actually quite remarkable in its own right. It shows that even in two dimensions, our intuitive understanding of area and decomposition can be completely wrong. The surface of a sphere contains enough room to be duplicated through clever rearrangement of its parts. Another interesting variation involves different geometric objects. While the classic Banach-Tarski paradox deals with balls, similar results can be proved for other shapes. Any two bounded sets in three-dimensional space that have non-empty interiors are equidecomposable using the Banach-Tarski method. This means you can take any such shape, decompose it into pieces, and reassemble those pieces to form any other such shape. For example, you could theoretically decompose a cube and reassemble it into a sphere of different size. You could take a teapot-shaped region and rearrange it into a dodecahedron. The specific shape doesn't matter as long as it's bounded and has non-empty interior. This generalization reveals that the Banach-Tarski paradox isn't really about spheres at all. It's about the fundamental properties of three-dimensional space and the pathological nature of non-measurable sets. The sphere is just a convenient example, but the underlying mathematical machinery works for any reasonable shape. There are also results that show the limitations of the Banach-Tarski method. For instance, the paradox works in 3 dimensions and higher, but not in 1 or 2 dimensions. In 1 and 2 dimensions, any decomposition that preserves congruence must also preserve measure. You can't duplicate a line segment or a disk using only rotations and translations. This dimensional dependence is related to the fact that free groups can act on spaces of dimension 3 and higher in ways that aren't possible in lower dimensions. The geometry of 3-dimensional space provides enough room for the complex group actions that make the paradox possible. Another fascinating extension involves the axioms of set theory. As we've discussed, the Banach-Tarski paradox depends on the axiom of choice. But mathematicians have investigated what happens if we modify or reject this axiom. In set theories that reject the axiom of choice, the Banach-Tarski paradox cannot be proved. This suggests that the paradox reveals something fundamental about the nature of choice and construction in mathematics. It's not just a quirky theorem. It's a window into the foundations of mathematical reasoning itself. Some mathematicians have proposed alternative axiom systems that avoid the counterintuitive consequences of Banach-Tarski while preserving most of the useful applications of the axiom of choice. These investigations have led to deep insights into the relationship between different mathematical frameworks and their consequences. There are also probabilistic versions of the Banach-Tarski paradox. Instead of dealing with arbitrary decompositions, these results consider what happens when we try to assign probabilities to the pieces involved in the construction. It turns out that the non-measurable nature of the pieces makes it impossible to define consistent probability measures for them. This connects the paradox to fundamental questions in probability theory and measure theory. It shows that our intuitive understanding of probability, like our understanding of volume and area, breaks down when we venture into the realm of non-measurable sets. Recent research has also explored connections between the Banach-Tarski paradox and other areas of mathematics and physics. For example, some researchers have investigated potential connections to quantum mechanics, where the nature of measurement and observation plays a crucial role. Others have looked at connections to computer science and complexity theory. While the Banach-Tarski construction can't be carried out algorithmically, understanding its structure has provided insights into the nature of computation and algorithmic construction. There are also ongoing investigations into the philosophical implications of the paradox. What does it mean for mathematical objects to exist? How should we understand the relationship between mathematical truth and physical reality? These questions go to the heart of the philosophy of mathematics and continue to generate debate and discussion. All of these variations and extensions show that the Banach-Tarski paradox isn't an isolated curiosity. It's part of a rich mathematical landscape that reveals deep truths about infinity, measurement, construction, and the foundations of mathematics itself. Understanding this broader context helps us appreciate not just the paradox itself, but its place in the larger story of mathematical discovery. The Banach-Tarski paradox raises profound philosophical questions that go far beyond mathematics. It challenges our basic understanding of space, reality, and the nature of mathematical truth itself. Let's explore some of these deeper implications. First, consider what the paradox tells us about the nature of mathematical objects. In our everyday experience, objects have definite properties. They have size, weight, location, and boundaries. When we cut something into pieces, the pieces have definite shapes and volumes. And when we put them back together, we get exactly what we started with, nothing more and nothing less. The Banach-Tarski paradox shows us that mathematical objects can behave very differently. The pieces in the construction don't have well-defined volumes or boundaries. They're scattered throughout space in ways so complex that they defy our geometric intuition. This raises the question, what exactly are mathematical objects, and how do they relate to physical objects? One perspective is mathematical Platonism, the view that mathematical objects exist in some abstract realm, independent of physical reality. From this perspective, the Banach-Tarski paradox reveals truths about this abstract realm that happen to be very different from the truths of the physical world. Mathematical spheres and physical spheres are different kinds of entities, so it's not surprising that they follow different rules. Another perspective is mathematical formalism, which holds that mathematics is just a game played with symbols according to certain rules. From this view, the Banach-Tarski paradox is simply a consequence of the rules we've chosen for our mathematical game. It doesn't tell us anything about reality. It just shows us what follows from our axioms and definitions. A third perspective is mathematical constructivism, which insists that mathematical objects must be explicitly constructible to be considered real. Constructivists reject the axiom of choice, precisely because it allows for non-constructive proofs like the Banach-Tarski paradox. From this viewpoint, the paradox doesn't describe anything real because the construction can't actually be carried out. The paradox also raises questions about the nature of infinity. Our everyday experience deals with finite collections of objects. When we have a finite set of things, we can count them, measure them, and understand their properties through direct observation. But infinite sets behave very differently, as the paradox dramatically illustrates. This connects to broader philosophical questions about whether infinity is a real feature of the universe or just a useful mathematical abstraction. Some philosophers argue that actual infinities don't exist in nature, only potential infinities that we can approach but never reach. Others contend that infinity is a genuine aspect of reality that we need to take seriously in our understanding of the universe. The Banach-Tarski paradox also illuminates the relationship between mathematical proof and physical possibility. Mathematics can prove statements that seem to contradict physical intuition, but this doesn't necessarily mean that mathematics is wrong or that physical intuition is always reliable. Instead, it suggests that mathematical truth and physical truth operate in different domains with different rules. This has implications for how we use mathematics in science. When physicists use mathematical models to describe natural phenomena, they need to be careful about which mathematical features correspond to physical reality and which are artifacts of the mathematical framework. The Banach-Tarski paradox serves as a reminder that not everything that's mathematically possible is physically realizable. The paradox also raises questions about the nature of space itself. In our everyday experience, space seems continuous and uniform. We can move smoothly from one location to another, and empty space appears to be the same everywhere. But the Banach-Tarski construction reveals that mathematical space has a much richer and stranger structure than our intuition suggests. This connects to ongoing debates in physics about the nature of space-time. Is space really continuous, or is it made up of discrete units at the smallest scales? Do the mathematical properties of space in general relativity correspond to physical properties of the universe, or are they just useful approximations? The Banach-Tarski paradox doesn't answer these questions directly, but it reminds us that space might be much stranger than we think. There are also implications for our understanding of measurement and observation. The paradox shows that some mathematical objects can't be measured in the usual sense. This raises questions about what it means to measure something and whether all aspects of reality are, in principle, measurable. In quantum mechanics, measurement plays a fundamental role, and there are ongoing debates about what happens during the measurement process. While the Banach-Tarski paradox doesn't directly relate to quantum measurement, it does show that our classical intuitions about measurement and decomposition can be deeply misleading. The paradox has also influenced discussions about the foundations of mathematics itself. Should we accept the axiom of choice despite its counterintuitive consequences? Are there alternative foundation systems that would avoid these problems while preserving the useful applications of mathematics? These questions continue to generate research and debate among mathematicians and philosophers. Finally, the Banach-Tarski paradox raises questions about the nature of explanation and understanding. We can prove that the paradox is true, and we can understand the mathematical machinery that makes it work. But in what sense do we really understand what's happening? The result is so counterintuitive that it challenges our usual notions of mathematical insight and comprehension. This connects to broader questions about the relationship between formal proof and genuine understanding. Is it enough to have a rigorous proof, or do we need some kind of intuitive grasp to claim real understanding? The Banach-Tarski paradox suggests that these two kinds of knowledge can sometimes diverge dramatically, while the Banach-Tarski paradox can't be directly applied to physical objects. Its mathematical insights have found surprising connections to other areas of mathematics and even some practical applications. Let's explore how this seemingly abstract result connects to the broader mathematical universe. One of the most important connections is to measure theory, the mathematical framework for assigning sizes, volumes, and probabilities to sets. The Banach-Tarski paradox reveals fundamental limitations of measure theory by showing that not all sets can be assigned meaningful measures. This has led to a deeper understanding of what kinds of sets can be measured and what kinds cannot. This understanding has practical implications for probability theory and statistics. When we work with probability distributions, we need to be careful about which sets we can meaningfully assign probabilities to. The existence of non-measurable sets revealed through results like Banach-Tarski helps us understand the boundaries of probabilistic reasoning. The paradox has also influenced the development of alternative theories of measurement. Some mathematicians have developed fini-added measures that can handle some non-measurable sets, while others have explored constructive approaches to measurement that avoid non-measurable sets entirely. These alternative frameworks have found applications in areas ranging from decision theory to quantum mechanics. In topology, the study of spatial properties that are preserved under continuous deformations, the Banach-Tarski paradox has led to insights about the structure of transformation groups, understanding which groups can act on which spaces, and how these actions can decompose objects has applications throughout geometry and topology. For example, these insights have been applied to the study of crystallographic groups, which describe the symmetries of crystal structures in materials science. While the specific pathological properties of the Banach-Tarski construction don't appear in crystal structures, the general theory of group actions that underlies the paradox does have practical applications in understanding material properties. The paradox has also influenced research in geometric group theory. It's a field that studies the geometric properties of algebraic structures. The free groups that play a crucial role in the Banach-Tarski construction are now understood as part of a broader landscape of groups with interesting geometric properties. Its research has applications in areas ranging from computer science to theoretical physics. In computer science, the study of algorithms and computational complexity has been influenced by insights from the Banach-Tarski paradox. While the paradox itself relies on non-constructive proofs that can't be turned into algorithms, understanding the limitations of constructive methods has helped computer scientists develop better algorithms for geometric problems. For example, research into computational geometry, which deals with efficient algorithms for solving geometric problems, has been informed by understanding which geometric constructions are computable and which are not. The Banach-Tarski paradox serves as an extreme example of a non-computable geometric construction. The paradox has also found connections to fractal geometry, the study of self-similar structures that appear at all scales. While fractals and the Banach-Tarski construction are different phenomena, both reveal the counterintuitive properties that can arise when dealing with infinite sets and recursive structures. Some researchers have explored whether fractal-like structures might provide models for understanding the pathological sets involved in the Banach-Tarski construction. While these connections are still being investigated, they suggest that the paradox might be part of a broader pattern of mathematical structures that challenge our intuitive understanding of space and dimension. In theoretical physics, the Banach-Tarski paradox has contributed to discussions about the nature of space and time. While the paradox doesn't directly apply to physical space-time, it has influenced how physicists think about the mathematical structures they use to model reality. For example, in general relativity, space-time is modeled as a smooth manifold, a mathematical structure that shares some properties with the three-dimensional space where the Banach-Tarski paradox applies. Understanding the limitations and pathological properties of such mathematical structures helps physicists be more careful about which features of their models correspond to physical reality. The paradox has also influenced discussions in quantum field theory, where infinite dimensional spaces and non-trivial group actions play important roles. While the specific construction of Banach-Tarski doesn't appear in quantum field theory, the general principles about how infinite dimensional structures can behave counterintuitively have informed research in this area. In mathematical logic and set theory, the Banach-Tarski paradox continues to be a testing ground for different foundational approaches to mathematics. Researchers use it to explore the consequences of different axiom systems and to understand the relationship between different mathematical frameworks. For example, investigations into whether the paradox can be proved without the full strength of the axiom of choice have led to discoveries about the relative strength of different mathematical principles. This research has practical implications for computer science, where understanding which mathematical principles are needed for which constructions can influence the design of automated theorem-proving systems. The paradox has also found unexpected connections to other areas of pure mathematics. In harmonic analysis, the study of how functions can be decomposed into simpler components, the group-theoretic techniques underlying Banach-Tarski have been applied to understanding the structure of function spaces. In algebraic topology, which studies the relationship between algebraic and topological structures, the paradox has contributed to our understanding of how different geometric constructions relate to algebraic properties. The free groups that make the paradox possible are examples of algebraic structures with interesting topological properties. Even in number theory, traditionally one of the most concrete areas of mathematics, the abstract techniques developed to understand the Banach-Tarski paradox have found applications. The study of how infinite groups act on various mathematical objects has contributed to research into Diophantine equations, the distribution of prime numbers, and other central problems in number theory. Perhaps most importantly, the Banach-Tarski paradox has served as a catalyst for mathematical education and outreach. Its counterintuitive nature makes it an excellent tool for demonstrating the difference between mathematical intuition and mathematical rigor. It shows students and the general public that mathematics can be surprising, even shocking, and that our everyday understanding of space and measurement may be much more limited than we realize. This educational value extends beyond mathematics itself. The paradox teaches important lessons about the nature of logical reasoning, the relationship between abstract models and concrete reality, and the importance of being precise about assumptions and definitions. These lessons are valuable in many fields, from science and engineering to philosophy and public policy. The paradox has also influenced the development of mathematical visualization and computer graphics. While we can't actually visualize the non-measurable sets involved in the construction, attempts to create visual representations of the underlying mathematical structures have led to advances in how we represent and interact with complex mathematical objects. Modern mathematical software systems, from computer algebra systems to theorem provers, have incorporated insights from the study of the Banach-Tarski paradox. Understanding which mathematical constructions are computable and which are not helps developers design better tools for mathematical research and education. Despite its mathematical rigor, the Banach-Tarski paradox is often misunderstood or misrepresented in popular discussions. Let's address some of the most common misconceptions and clarify what the paradox actually says and doesn't say. Misconception number 1. The paradox proves that mathematics is inconsistent or contradictory. This is absolutely false. The Banach-Tarski paradox is a perfectly valid theorem that follows logically from accepted mathematical axioms, particularly the axiom of choice. It doesn't reveal any logical contradictions in mathematics. It reveals that our intuitive understanding of space and volume can be misleading when applied to infinite sets. The term paradox in mathematics doesn't mean contradiction. It means a result that contradicts common intuition. Many mathematical paradoxes, from Zeno's paradoxes in ancient Greece to modern results like Banach-Tarski, are actually rigorous theorems that reveal the limitations of our intuitive understanding rather than problems with mathematical reasoning. Misconception number 2. The paradox could be used to create infinite energy or matter. This misunderstanding confuses mathematical objects with physical ones. The paradox applies only to abstract mathematical sets, not to physical objects made of atoms and molecules. As we discussed earlier, physical objects have properties like mass and energy that must be conserved according to the laws of physics. Even if we could somehow apply the mathematical construction to physical objects, we would need to account for all the physical properties of the matter involved. The mathematics tells us nothing about how to do this, because it operates at a level of abstraction where these physical properties don't exist. Misconception number 3. The paradox shows that the axiom of choice should be rejected. While some mathematicians have argued this position, it's not a necessary conclusion. The axiom of choice is incredibly useful for proving important theorems throughout mathematics, and most working mathematicians accept it despite its counterintuitive consequences. The fact that an axiom leads to surprising results doesn't automatically mean the axiom is wrong. Instead, it might mean that our intuitions are limited, or that we need to be more careful about how we apply mathematical results to the physical world. Misconception number 4. The pieces in the Banach-Tarski decomposition have strange shapes or bizarre geometric properties. Actually, the pieces don't have shapes in any meaningful sense. They're not geometric objects with boundaries and surfaces. They're abstract sets of points defined by their relationship to certain group actions. These sets are so pathologically constructed that they don't have well-defined geometric properties like volume, surface area, or even recognizable shapes. They're distributed throughout space in ways so complex that they can't be visualized or physically realized. Misconception number 5. The paradox applies to all mathematical decompositions. This is false. The paradox requires very specific conditions: three-dimensional space, the axiom of choice, and the particular group-theoretic construction we described. It doesn't apply to one- or two-dimensional objects. And it doesn't apply to decompositions that don't use the specific mathematical machinery involved in the proof. Most mathematical decompositions, even in 3 dimensions, preserve, measure, and behave according to our intuitive expectations. The Banach-Tarski construction is special precisely because it exploits very particular pathological properties of certain mathematical objects. Misconception number 6. The paradox means that volume or measurement is meaningless in mathematics. This goes too far. The paradox shows that not all sets can be assigned meaningful measures, but many sets can be. The mathematical theory of measurement, called measure theory, is a well-developed and useful framework that handles the vast majority of mathematical objects we encounter. The existence of non-measurable sets doesn't invalidate measurement theory any more than the existence of irrational numbers invalidates arithmetic. It just shows that we need to be careful about the domain of applicability of our mathematical concepts. Misconception number 7. The paradox is just a mathematical curiosity with no broader significance. While it's true that the paradox can't be directly applied to solve practical problems, it has had profound influence on multiple areas of mathematics and our understanding of mathematical foundations. As we discussed in the previous chapter, insights from the paradox have influenced research in areas ranging from computer science to theoretical physics. It's also been crucial for understanding the relationship between different axiom systems and the nature of mathematical reasoning itself. Misconception number 8. If you understand the proof, you should be able to visualize or intuitively grasp what's happening. This expectation is unrealistic. The Banach-Tarski construction involves mathematical objects so abstract and pathological that they can't be visualized or understood through geometric intuition. Understanding the proof means following the logical steps and seeing why each step is valid. It doesn't require being able to picture what's happening in any intuitive sense. This is actually a common feature of advanced mathematics. Rigorous understanding often involves accepting conclusions that go beyond what we can visualize or intuitively grasp. Misconception number 9. The paradox shows that infinity is impossible or meaningless. Some people react to the counterintuitive properties of infinite sets by concluding that infinity itself is problematic. However, infinite sets are well-defined mathematical objects that follow consistent logical rules, even when those rules lead to surprising consequences. The strangeness of infinite sets doesn't make them meaningless any more than the strangeness of quantum mechanics makes atoms meaningless. It just means that infinite objects behave very differently from finite ones, and we need to adjust our expectations accordingly. Misconception number 10. The paradox proves that space itself has these strange properties. The paradox applies to mathematical models of space, not necessarily to physical space itself. Physical space might be discrete at small scales. It might not satisfy the mathematical axioms needed for the paradox, or it might have other properties that prevent the construction from being realized. The relationship between mathematical models and physical reality is complex and continues to be investigated by physicists and mathematicians. The Banach-Tarski paradox reminds us to be careful about this relationship, but it doesn't settle questions about the nature of physical space. Understanding these misconceptions is crucial for appreciating what the Banach-Tarski paradox actually teaches us. It's a profound result that reveals deep truths about mathematical infinity, the foundations of measurement, and the relationship between mathematical abstraction and physical reality. But it's not magic, and it doesn't break the laws of physics or logic. The Banach-Tarski paradox belongs to a rich tradition of mathematical paradoxes that have shaped our understanding of logic, infinity, and the foundations of mathematics. To fully appreciate Banach-Tarski, it's helpful to see how it fits into this broader landscape of counterintuitive mathematical results. One of the earliest and most famous mathematical paradoxes comes from ancient Greece: Zeno's paradoxes of motion. Zeno argued that motion is impossible because to travel from one point to another, You must first travel half the distance, then half the remaining distance, then half of what remains, and so on infinitely. Since you can't complete infinitely many tasks in finite time, Zeno concluded, motion is impossible. Of course, we know that motion is possible, but Zeno's paradoxes revealed deep problems with ancient Greek understanding of infinity and continuity. These paradoxes weren't resolved until the development of calculus and modern theories of infinite series in the 17th and 18th centuries, like the Banach-Tarski paradox. Zeno's paradoxes showed that mathematical reasoning could lead to conclusions that seemed to contradict common sense. In the late 19th century, mathematicians encountered a new class of paradoxes related to infinite sets and the foundations of mathematics. The most famous of these is Russell's paradox. Discovered by Bertrand Russell in 1901, Russell asked, "Is the set of all sets that don't contain themselves a member of itself? If it is, then it shouldn't be. If it isn't, then it should be." This simple question revealed a fundamental contradiction in naive set theory. Russell's paradox forced mathematicians to completely reconstruct the foundations of set theory and mathematical logic. This led to the development of axiomatic set theory, including systems like Zermelo-Fraenkel's set theory with the axiom of choice, which provides the foundation for the Banach-Tarski paradox. Another influential paradox from this period is Cantor's paradox, which deals with the supposed set of all sets. Georg Cantor had proved that for any set, the set of all its subsets has larger cardinality than the original set. But if you apply this theorem to the set of all sets, you get a contradiction. The set of all sets should be the largest possible set, but its power set should be even larger. Like Russell's paradox, Cantor's paradox showed that unrestricted set formation leads to contradictions. The resolution is that there is no set of all sets in standard set theory. Some collections are too large to be sets. They're called proper classes instead. These foundational paradoxes created what historians call the crisis of foundations. In mathematics around 1900, mathematicians realized that their intuitive understanding of mathematical objects wasn't sufficient for the level of rigor they were trying to achieve. This crisis led to major developments in mathematical logic, set theory, and the philosophy of mathematics. The Banach-Tarski paradox, proved in 1924, came out of this foundational work. Unlike Russell's paradox or Cantor's paradox, Banach-Tarski doesn't reveal an actual contradiction in mathematics. Instead, it reveals the counterintuitive consequences of accepting certain mathematical principles, particularly the axiom of choice. Another famous paradox from this period is the Skolem paradox, which deals with models of set theory. Leopold Lewenheim and Thoralf Skolem proved that any first-order theory that has an infinite model also has a countable model. Applied to set theory, this seems to imply that there's a countable model of set theory, even though set theory proves the existence of uncountable sets. The resolution of the Skolem paradox involves understanding the difference between different notions of countable and the limitations of first-order logic. Like the Banach-Tarski paradox, it reveals subtle distinctions that aren't apparent from naive reasoning. In the 20th century, mathematicians discovered many other counterintuitive results that challenge common sense while being perfectly rigorous. For example, there are space-filling curves, continuous functions that map the unit interval onto the entire unit square. Giuseppe Peano discovered the first such curve in 1890, showing that our intuitive understanding of dimension can be misleading. Another example is the intermediate value theorem in a pathological setting. While the theorem guarantees that continuous functions on intervals have certain nice properties, there exist continuous functions that are nowhere differentiable. These functions are continuous everywhere, but have no well-defined slope at any point, defying geometric intuition. In topology, there are results like the Banach-Mazur theorem, which states that every separable Banach space can be embedded in the space of continuous functions on the unit interval. This means that abstract infinite-dimensional spaces can be represented as spaces of functions in ways that aren't geometrically obvious. The study of fractals has revealed objects with non-integer dimensions, infinite perimeters enclosing finite areas, and other properties that challenge traditional geometric thinking. The Mandelbrot set, Julia sets, and other fractal objects exhibit infinite complexity at arbitrarily small scales. In probability theory, there are paradoxes like the Bertrand paradox, which shows that probability can depend crucially on how you set up a problem. Different reasonable approaches to the same question can yield different answers, revealing the subtle nature of probabilistic reasoning. Modern mathematics continues to produce results that challenge intuition. In algebraic topology, there are objects called exotic spheres, manifolds that are homeomorphic to spheres, but not diffeomorphic to them. In other words, they have the same topological structure as ordinary spheres, but different smooth structures. In set theory, researchers have discovered that many important mathematical questions are undecidable. They can't be proved or disproved from the standard axioms of mathematics. The continuum hypothesis, which asks whether there are sets larger than the integers but smaller than the real numbers, is the most famous example. What all these paradoxes and counterintuitive results share is that they reveal the limitations of human intuition. When dealing with mathematical infinity, abstract structures, and rigorous logical reasoning, they show that mathematics is not just formalized common sense, but a discipline that can lead us to truths that go far beyond everyday experience. The Banach-Tarski paradox fits perfectly into this tradition. Like Zeno's paradoxes, it reveals problems with naive reasoning about infinity. Like Russell's paradox, it emerges from careful analysis of set theory and the foundations of mathematics. Like the various geometric and topological paradoxes, it shows that mathematical space can behave in ways that defy physical intuition. Understanding this broader context helps us appreciate that the Banach-Tarski paradox isn't an isolated anomaly. It's part of a rich tapestry of mathematical results that push the boundaries of human understanding and reveal the deep structure of mathematical reality. As we reach the end of our journey through the Banach-Tarski paradox, it's worth reflecting on what this remarkable theorem teaches us about mathematics, reality, and the nature of human understanding. First and foremost, the paradox teaches us about the power and limitations of mathematical reasoning. Mathematics is incredibly powerful. It can prove statements that seem impossible, reveal hidden connections between seemingly unrelated ideas, and provide insights that go far beyond common sense. The fact that mathematicians can rigorously prove that one ball can become two balls, even though this seems physically impossible, demonstrates the remarkable reach of mathematical logic. But the paradox also reveals the limitations of mathematical reasoning when applied to physical reality. Not everything that's mathematically possible is physically realizable. The abstract mathematical objects that mathematicians study don't always correspond directly to objects in the physical world. This is an important lesson for anyone trying to apply mathematics to understand nature. The paradox teaches us about the nature of infinity and how infinite sets behave differently from finite ones. In our everyday experience, we deal with finite collections of objects, and our intuitions are well adapted to this finite realm. But infinite sets follow different rules, and these rules can lead to consequences that seem absurd from a finite perspective. This has broader implications for how we think about the universe. If the universe is infinite in space or time, or if it contains infinite quantities of matter and energy, then our finite intuitions might be inadequate for understanding its true nature. The Banach-Tarski paradox serves as a reminder that infinity is not just a very large number, but something qualitatively different that requires different conceptual tools. The paradox also teaches us about the importance of being precise about our assumptions and definitions. The counterintuitive conclusion follows rigorously from specific mathematical axioms, particularly the axiom of choice. This shows how small changes in our foundational assumptions can have dramatic consequences for what we can prove and what we consider true. This lesson extends beyond mathematics to other areas of human inquiry. In science, philosophy, politics, and everyday life, our conclusions depend crucially on our starting assumptions. The Banach-Tarski paradox reminds us to be explicit about these assumptions and to think carefully about their implications. The paradox teaches us about the relationship between mathematical proof and intuitive understanding. We can have a complete, rigorous proof of a mathematical statement while still finding it impossible to visualize or intuitively grasp what's happening. This suggests that there are different kinds of understanding, and that formal logical understanding doesn't always align with intuitive geometric understanding. This has implications for mathematics, education, and communication. Sometimes the best we can do is help people follow the logical steps of a proof, even if the conclusion remains counterintuitive. This is perfectly acceptable and doesn't represent a failure of understanding. The paradox also teaches us about the nature of space and measurement. Our everyday understanding of space as something that can be divided into well-defined pieces with definite volumes turns out to be more limited than we might expect. Mathematical space has a richer and stranger structure that allows for decompositions that don't preserve measure. While this doesn't directly tell us about the nature of physical space, it does suggest that space might be more complex and interesting than our everyday experience suggests. This is relevant to ongoing research in physics about the fundamental nature of space-time. The paradox teaches us about the role of choice and construction in mathematics. The axiom of choice allows mathematicians to make infinitely many arbitrary choices simultaneously, leading to constructions that seem impossible. This raises deep questions about what it means for mathematical objects to exist and whether all logically consistent mathematical statements correspond to meaningful mathematical truths. These questions connect to broader philosophical issues about the nature of existence, reality, and truth. The Banach-Tarski paradox doesn't settle these issues, but it provides a concrete example that sharpens our thinking about them. The paradox also teaches us about the importance of intellectual humility. Even very smart people with extensive mathematical training find the result counterintuitive and difficult to accept emotionally, even while understanding it intellectually. This suggests that human intuition, no matter how well developed, has limitations when dealing with abstract mathematical concepts. This lesson applies beyond mathematics. In any field of inquiry, we should be prepared for the possibility that reality is stranger and more complex than our intuitions suggest. Being open to counterintuitive ideas while still maintaining appropriate skepticism is crucial for intellectual progress. Finally, the paradox teaches us about the beauty and wonder of mathematics itself. Despite its counterintuitive nature, or perhaps because of it, the Banach-Tarski paradox is a thing of mathematical beauty. It reveals unexpected connections between different areas of mathematics, demonstrates the power of abstract reasoning, and opens up new questions for investigation. The fact that such a result is possible reminds us that mathematics is not just a tool for practical problem solving, but a vast and largely unexplored territory full of surprises and wonders. Every mathematical theorem, no matter how abstract, adds to our understanding of this territory and reveals new landscapes for future exploration. In closing, the Banach-Tarski paradox stands as one of the most remarkable achievements in mathematical history. It challenges our understanding of space, infinity, and reality itself. It reveals the power and limitations of mathematical reasoning. It connects abstract mathematical concepts to deep philosophical questions about the nature of existence and truth. Most importantly, it reminds us that the universe of mathematical ideas is far richer and stranger than we might expect. In a world where one ball can become two balls through the magic of mathematical reasoning, who knows what other wonders await discovery? Whether you're a student just beginning to explore advanced mathematics, a researcher pushing the boundaries of human knowledge, or simply someone curious about the deepest patterns underlying reality, the Banach-Tarski paradox offers profound lessons and endless fascination. Mathematics may not always align with our physical intuitions, but it provides us with tools for exploring realms of possibility that extend far beyond the everyday world. In doing so, it expands our conception of what's possible and enriches our understanding of the deep structures that govern both mathematical and physical reality. The Banach-Tarski paradox will continue to puzzle, inspire, and educate future generations of mathematicians, scientists, and curious minds. It stands as a testament to the power of human reasoning and a reminder that reality, whether mathematical or physical, is far more wonderful and strange than we might ever have imagined. Thank you for joining me on this journey through one of mathematics' most fascinating paradoxes. If you enjoyed this exploration, make sure to subscribe for more deep dives into the most mind-bending concepts in mathematics and science. Until next time, keep questioning, keep wondering, and remember that in the infinite realm of mathematical possibility, even the impossible becomes inevitable.